Hello, this week we're going to talk about triangles. Now, this is going to be a bit of a longer lesson, have fun, I guess. So, first, let's start with classifying triangles. We already. First, acute triangles, that's where all angles are less than 90 degrees. Right triangles, that's when you have one 90-degree angle in the entire triangle. And then you have obtuse triangles, where you have one angle that is more than 90 degrees. Uh, and that's classifying triangles by angle. If you're classifying them by side, then equilateral triangles, that's when all three sides have the same length, and that means that all angles have to be 60 degrees. And next are isosceles triangles, when you have two sides that are the same length. And when that's true, this angle and this angle are the same. And then you have scalene triangles, which are just when all three sides have different lengths. And if that happens, that means all three angles also have different measures. Now let's try breaking down a triangle. Let's say we have a triangle ABC. Now, usually we don't denote this side as A, this side as B, and this side as C. Or you can say that C equals AB, B equals AC, and A equals BC if we're just talking about sides. Now, putting this thing aside, the next part of the triangle is the median. Now, if we take a line from the vertex and draw it to the center of the opposite side, that is known as the median. And if we draw all three medians like this point here where they intersect, this is known as the centroid. And note that it is not necessarily the center of the triangle, but let's just label these. Okay, so this point, let's call it F, this point, let's call it D, and this point, let's call it E. And the point in the center, it's usually called G. So we have AG over GD. This is equal to BG over GE, which is equal to CG over GF, which is equal to 2 to 1. So basically the ratio from here to here to here to here, it's always equal to 2 to 1. The ratio from like the centroid to 1 to the vertex is always twice the distance from the centroid to the opposite side. Now, is something that I probably should have mentioned before. The perimeter of the triangle is AB plus BC plus CA, which is just basically the sum of all sides, and the semi-perimeter, which is half the perimeter, which is usually denoted as S, that's just the sum of all sides divided by 2. And that's pretty much only important because of a few formulas. Now, the next thing to talk about is angle bisectors. Now, I can't remember if I had this lesson before, but if you have an angle and then you just cut it in half, and then continue this line here, that's an angle bisector. And if we draw the angle bisectors of all three, okay, that was drawn badly, but draw the angle bisectors of all three, they will always meet at one point. And there is a proof for this, but I don't really have time to go through it. And just as a note, as you can see, like from this not very scale diagram, but this here and here are really the same length, which means that the angle bisector is not necessarily the same as the median. Now, like I said, this isn't really drawn to scale, But if it was drawn to scale, the distance from here to here, here to here, and here to here are supposed to be equal. And if you draw a circle inscribed within the triangle, the center of the circle should be the point where the lines intersect, which is denoted as I. So to reiterate, even though it doesn't really look like it in this diagram, if you take the angle bisector of all three angles of a triangle, which basically means you split the angle in half, and then you find the point where they meet, that will be the center of a circle, which can be inscribed within a triangle. Now the circle, if it's inscribed inside a triangle, this is known as an incircle. Yes, very clever name. And the center of the circle is known as the incenter, and then the radius of the circle is known as the inradius, because you know what, mathematicians like to name stuff like that, I guess. Next we have what's known as a perpendicular bisector. Basically, if we take the midpoint of this segment here, where both sides have the same length, and you just draw a line perpendicular to it, so 90 degrees, that's known as the perpendicular bisector. And the perpendicular bisector is always equal distance from both of these points here, which is the edges of the segment. It's always the same distance from the. So from here is the same distance from here to here and here to here. Here, the same distance from here to here, here to here, and so on. Now, anyways, if we take this triangle and basically draw a circle around it, we say that we have circumscribed this triangle, and like always, the center of the circle is the circumcenter, the circle itself is called the circumcircle, and then the radius is called the circumradius. Next in our lesson about triangles is the altitude, or basically the height. If we take a triangle and basically just draw a line like this, from basically the base of the triangle to the highest point here, perpendicular here, this is known as the altitude or the height, which is just usually denoted as an h. Now next, let's finally go into some rules of triangles. Let's start with something completely obvious. So let's say you have a triangle A, B, and C. Now, what are the possible values of the sides? Well, you don't have any information, let's give you some. Let's say that A is equal to 11, B is equal to 15, so what could C be? Well, let's start with something. Let's say, can C be equal to 26? Well, first of all, maybe you just start thinking, of course it can, but then consider this. If A and B are 11, 15 respectively, that means added together it's 26, and that means C would be the same length as A and B combined, which would mean it would be a very awkward straight line and not really go at all. Sorry, started there a bit. But yeah, basically, like I said, if C is equal to or greater than A plus B, that's not a possible triangle. Now, using the same logic, can we say that C is something smaller? Can we say that C equals 1, maybe? Well, let's look at it here. If we added C and A together, then that would be 12, and B is obviously a lot bigger than 12, so that would also be impossible. So that means C has to be less than A plus B. A has to be less than C plus B, and B has to be less than A plus C. Well, that might seem completely obvious to you now that I've mentioned it. It's still something that some people occasionally get wrong for some reason. And that it's just basically common sense. Now, let's go with good old Pythagoras. Now, sometime in Greece, some dude named Pythagoras decided to make a theorem. He said, in a right triangle with sides A, B, and C, A squared plus B squared equals C squared, and that will always be true as long as it is a right triangle. And honestly, other than that, there's not really too much you can know. You need to know what you can say something like B squared is equal to C squared minus A squared. Gasp. And if you don't want to do the squared thing, you can just get the square root of everything. Gasp. And there's also a thing called Pythagorean triples, which are a set of integers A, B, C, which basically follow A squared plus B squared equals C squared. Now, some common ones are 3, 4, 5, 7, 24, 25, 8, 15, 17. You're not really expected to memorize them. 3, 4, 5 is probably the easiest. But occasionally it's just easier that way. Also note that 6, 8, 10 is also a Pythagorean triple. And so is 9, 12, 15. And really the general rule is that if some set of integers A, B, C are a set of Pythagorean triples, so they follow this rule, then a set of integers NA, NB, NC will also be a set of Pythagorean triples. And honestly, this is quite easy to prove, so I won't really go into it. As for the proof for the Pythagorean theorem, there is one, but not really going to go into it too much, but you can search it up if you're interested. Next on our list to talk about is congruent triangles. Now, congruent basically means that they're exactly the same. So if I have some triangle A, B, C, and some triangle D, E, F, and this side is equal to this side is equal to this side is equal to this side, and all the angles are also the same, well, we say they're congruent, or basically identical. Just imagine you take a triangle and clone it. Now, there's a few ways to prove congruence. First of all, if the three sides are the exact same length, so like A, B, wait, actually that's not how you're supposed to label them. A, B, C, D, E, F. If A equals D, E equals B, and C equals F, then they have to be congruent. We call this side congruence. Now if A equals D and B equals E, so if that's true and the angle here are also the same, so angle BCD is equal CD equals EFD. If that's true, then it's also similar, and this is known as side angle side congruence. Now also if A equals D, BCD equals EFD, and also these angles are the same, so if ABC equals EF, this will also be congruent, and this is known as angle side angle congruence. And keep in mind that if it's a right triangle, one angle is automatically 90 degrees, so then you have a free angle for any of these congruence theorems. Next, not congruence, now we have sort of the little brother, which is similar. So let's imagine you take a triangle, and instead of just cloning it directly, let's say you take a picture of it. Now, if you take a picture of an object and look at the actual object, well, obviously the size is different, and this is the same for similar triangles. So basically, if you take this and just make it bigger, um, it's essentially the same triangle, it just one of them is bigger than the other. Now, the ratio between the sides are equal, and the angles are equal. Uh, oh yeah, and I forgot to mention, for here for congruence, we say A, B, C. The symbol for congruence is the equal with the squiggly thing. And then this, the symbol for similarity is just the squiggly thing without the equal. So A, B, C is similar to D, E, F. And I'll just label it here. Now, similarity is a bit easier to prove. First off, you can just prove all sides, how the ratio between the sides are equal. That's automatically similar. Also, if you prove all angles are equal, that's also similarity. Next, if all three angles are the same, it's similar. But that means if you just take two angles, and they're equal to this, the equivalent on the other side, then they're also similar because, like, some of the angles has to be 180 degrees. And if an angle here and then like the two sides here, and this angle, if the angle is the same as this angle here, and then these sides are also in the same ratio, they're also similar there. And really, it's just the same rules as congruence, except instead of having the exact same side, you just have to have the same ratio of sides. And obviously, if two triangles are congruent, that means they're also similar, because you're just copy and pasting it, except you're just not doing anything with it. Next, let's have an introduction to trigonometry. Let's take a right triangle here. And I'll label it A, B, C. This is the right angle. Okay, first of all, this side C, the long side, that's called the hypotenuse. And let's just take an angle here. Let's call this A. Now, sine A is equal to opposite over hypotenuse. And opposite is the side opposite here. Hypotenuse is C, so then that would be equal to A over C. Cosine is equal to adjacent over hypotenuse, and adjacent is just the adjacent side here, so that would be B over C. And tangent, this is different than like a tangent line, it's a trig thing. That's equal to opposite over hypotenuse, so A over B. And then we have some other things. The second, that is equal to the hypotenuse over the adjacent. So basically the opposite of the cosine, or it's C over B. We have the cosecant, or which is basically 1 over the reciprocal of sine A, or C over A. And then finally we have the cotangent, which is the reciprocal of tangent, or it's also equal to B over A. And keep in mind we're referring to this diagram here. Now, even though we're getting these ratios from right triangles, it does apply to no matter what, as long as it's the same angle. So as long as we have the angle of measure A, let's say this is, I don't know, 35 degrees. As long as we have an angle of 35 degrees, these ratios will always be the same, even if it's not really a right triangle anymore. Now, why is this important? Well, honestly, we don't really have time to go over this. We might do it in a later lesson. But just know a few rules. Um, so if this is A, that means this is B. And sine A is equal to cos B. And that's when B is equal to 90 minus A. Because the remaining angle is 90 degrees, so then all that's left is 90. Also, sine squared A plus cos squared A is equal to 1, and A can just be any angle. Oh yeah, also, the reason we notate like sine squared, that's basically means this. Except it's sometimes annoying to have brackets, so we just put the squared symbol here instead. Just so we don't mix it up with sine A squared like this. And then the final rule is if sine A equals sine B, that means A equals B, at least assuming that we're working with angles that are less than 90 degrees. Now let's start working with some special angles. Imagine you have a square, and now imagine you cut the square in half. After we cut the square in half, well, this is obviously 90 degrees, and then these are both 45 degrees. And these sides are equal, so let's just call it 1, 1. And if we take Pythagoras, 1 squared plus 1 squared equals c squared, and then c squared would just be the square root of 2. So then if that happens, that means sine 45 is equal to opposite over hypotenuse, or 1 over square root of 2, or square root of 2 over 2. And then cosine 45 is also the same because both of these are 1, so it's also equal to square root of 2 over 2. And then tan 45 is equal to 1 because tan is opposite over adjacent, or 1 over 1. Also, just as a side note, somewhat mnemonic to remember that is SOHCAHTOA. So sine is equal to opposite over hypotenuse, cosine is equal to adjacent over hypotenuse, and tan is equal to opposite over adjacent. That's just a simple mnemonic here. Now, the next set of special angles, let's imagine an equilateral triangle, and now you cut this in half too. So this would be 30, this would be 60, this would be 2, 1, and let's see, Pythagoras, a squared plus b squared equals c squared. That means this is square root of 3. Now that means sine 30, that's opposite over hypotenuse. That would be 1 over 2, and that's also equal to cosine 60. Next we have cosine 30, which is also equal to sine 60, which is equal to cosine adjacent over hypotenuse, which is square root of 3 over 2. Finally, we have tan 30 equals opposite over hypotenuse, opposite over adjacent, or square root of 3 over 3, and tan 60, which is just equal to square root of 3. And now finally, just some generic ones. Sine 0 equals cosine 90 equals 0. Cosine 0 equals sine 90 equals 1. And tan 0 equals 0, and tan 90 doesn't exist. And the last thing we'll go into is the area of a triangle. Now, there's a few ways to do it. First, area is equal to 1/2 base times height. Now, what does that mean? Now, let's take some random triangle. The base here is b. The height is just from here to here. So basically the altitude or height. Now, how can you prove this? Basically just take a triangle, draw a square around it. Cut this here, you'll see that the area here is equal to area here is equal to area here, more or less. So it's just square, so base times height, but divided by 2 because you cut the square in 2. Next, you have area equals AB sine C all over 2. So if you have a triangle, it doesn't even have to be a right triangle, to be honest. Then you have A, B, C, and then this is angle C. So A times B times sine of the angle C here divided by 2. That is the area of the triangle. Then finally, we have area equals in radius times the semi-perimeter. And if you have forgotten, the in radius is, if we take a triangle here, inscribe a circle within it, pretend that this is inscribed properly, and the center of the circle, the distance from the center to one of the edges, that's equal to the in radius. Or you can also get the in radius from getting the angle bisector of these three sides, these three angles, and then finding the point where it meets. But it's sometimes easier just to draw a circle, but honestly at that point it's usually given to you. And then the semi-perimeter, in case you don't remember, that's equal to A plus B plus C divided by 2. And actually it just occurred to me that there's a third way to find area that I haven't mentioned. So if we take this triangle ABC, and then we say the semi-perimeter is S, then area is also equal to the square root of S times S minus A times S minus B times S minus C. And since this lesson has been a bit long, I'll just end you with one question. I'll be nice. You have a triangle A, B, A, B, C, and this is a right triangle. Now we have the midpoint here, we'll call it F. And let's also say that oh, I actually messed this up. No. We'll say that the hypotenuse is AC, and let's say that AB is equal to 3BC. Now let's add 2 more points here. D and E, and it's split in a way so that AB is split into three segments with the same length. And prove that triangle DFE is isosceles and right angled. And now I have that drawn it out, I realized I have messed up. Sorry, in this diagram, D and F aren't supposed to be here, they're supposed to be here. So yeah, now prove that this is a right angle and that this is an isosceles triangle. Anyways, have